Hello and welcome to Sleepy Scientist. I'm glad you're here, whether you've had a long day, a busy mind, or you simply love falling asleep to the sound of science. Tonight we're heading upward, far above rooftops beyond the clouds, into a dome of velvet blackness where tiny lights glitter and glow. You're lying back under a night sky still and wide, and all around you stars are winking, flickering, shimmering like candlelight through water. Some seem to dance, others hold steady. And then there, just above the horizon, you spot a different kind of light. Brighter, unblinking, almost calm. That's no star, it's a planet. And it's not twinkling at all. Why? Why do stars seem to shimmer, like secrets being whispered through the air, while planets shine like quiet thoughts? You trust completely. What's happening between you and those lights in the sky that causes one to dance and the other to sit still? Tonight, we'll drift gently through the answers. If you enjoy these sleepy explorations, I'd be so grateful if you gave the video a little like and tap that subscribe button. It helps more sleepy scientists like you find their way here, and it means I can keep making more of these journeys for you now. So now you let your head rest your breathing. Slow, your gaze float just above the edge of sleep. And above that, the stars begin to blink. You might think at first glance that twinkling is a sign of a star's instability, like it's fluttering or even changing. But the truth is the stars themselves are steady. Out there, light flows from them in vast, unbroken streams. Many have burned with perfect regularity for billions of years, their glow unchanged, whether we're watching or not. It's here on Earth where the drama begins. The moment that starlight enters our atmosphere, it begins to bend. It bends, wobbles, scatters, as if the air were a living lens, constantly warping and adjusting, like a giant piece of stained glass that never stops trembling. Have you ever looked at your hand through the surface of a swimming pool? The light shifts, edges dance, details ripple. That's exactly what the atmosphere does to the stars. It warps the light ever so slightly, many times a second. And because stars are so unimaginably far away, their beams of light are essentially pinpoints by the time they reach us. Just one tiny pencil of brightness trying to reach your eyes from trillions of kilometers away. That's what makes them so sensitive, so fragile, so twinkly. But not all of them twinkle equally, do they think about it? Have you ever stared at a particularly bright star, only to notice it changing colors, white to red to blue in a flicker? Have you ever wondered whether the star itself is unstable, or whether your eyes are being tricked by something else? Could it be the air, or your eyes, or both? As the light from stars enters the shifting layered atmosphere, it gets refracted, a fancy word for bent in a different direction. And when those refractions happen rapidly, due to turbulence in the atmosphere, you perceive that movement as a twinkle. The scientific name for this is stellar scintillation, a term that sounds a bit like fairy dust in a textbook. It means that what you're seeing isn't the star flickering, but the path of light flickering as it wiggles through air pockets of varying temperature, pressure, and density. The atmosphere acts like a restless river above your head, moving faster in some places, slower in others. Cold air slides past warm air. Moisture mixes with dryness. All these shifting currents bend light unpredictably. The result, that lovely sleep-inducing twinkle. But here's where things get cozy in the best kind of nerdy way. When you look at a planet, even though it's much closer than a star, it still appears star-like to the unaided eye. Just a bright dot. So, why doesn't it twinkle too? Well, the secret lies in size. Not how big the object really is, but how big it appears in the sky. A star, despite being hundreds of times larger than a planet, is so far away that it projects only a single point of light into your eye. That's it. One thread of brilliance easy for the atmosphere to toss around like a firefly in a wind tunnel. But a planet, though much smaller in reality, is close enough to appear as a tiny disk, a small surface, not just a point. That means the light reaching you isn't coming from a single path. It's arriving from many slightly different angles across the disk. And when the atmosphere jostles that light, the changes from one part of the disk often cancel out the others. The result, a steadier, calmer glow. So the reason planets don't twinkle like stars is because they're close enough to show some size, and that size offers stability. It's like trying to make a large lantern flicker by blowing on it. You'd have to blow very hard. But a candle, a single puff, and it dances. Isn't that a lovely way to think about it? Stars are the candles, delicate, distant, and easy to sway. Planets are the lanterns, anchored, quiet, glowing steadily across the dark. So next time you look up and see one light trembling while another stays still, you'll know. You'll know it's not magic or mystery. It's the air, it's distance, it's light being shaped by a living sky. And somehow that makes it all the more magical. Now let's float gently upward, shall we? Imagine your body lighter than air, lifting softly like a soap bubble through the night. You rise above the rooftops beyond the tree line, past the peaks of mountains. And then there it is, the sky that breathes. You may not see it, but you feel it. A vast, invisible ocean wrapped around the earth, always in motion, always whispering. This is the atmosphere, your planet's ever-shifting shawl of gas and temperature, and it is the reason stars twinkle. It's easy to forget that when you look up at the stars, you're looking through a fluid, not a solid dome, not empty space, but a swirling, breathing ocean of air made of nitrogen, oxygen, water, vapor, and countless microscopic whispers. And this air isn't still. It never is. From ground to sky, the atmosphere stacks itself in layers. The troposphere hugs the surface. This is where you live, where clouds drift, and birds soar, and storms are born. Above it comes the stratosphere, the mesosphere, the thermosphere, and beyond. Each layer with its own temperature, its own movement, its own agenda. And as starlight travels through these ever-changing veils, it becomes distorted. Let's picture it. A beam of starlight enters Earth's atmosphere like a note being sung across a crowded room. The air it moves through isn't uniform. Some parts are warmer, some cooler. Warm air expands and has a lower density. Cold air contracts and bends light differently. So as that single fragile beam moves down toward your eye, it gets refracted over and over again. Bent slightly here, twisted gently there. And the result, the star appears to dance. But here's the beautiful part, each twinkle is unique. The specific path the light takes changes from one moment to the next, often hundreds of times per second. You don't see each little bend, your brain can't separate them, but it does notice the variation. So what your eye sees is motion, flickering, sparkling. Sometimes it even shifts in color. That same turbulence causes a form of chromatic dispersion, which is just a lovely way of saying that different colors of light bend at slightly different angles. So as air ripples past between you and a star, you might briefly see its light change from bluish to reddish, and back again, like the universe itself is playing with a prism. Ask yourself, have you ever seen a star twinkle red for a heartbeat, then flash white again, or shimmer like a jewel spinning in place? Now you know it's the breathing sky playing tricks with physics. And that sky, it never sleeps. During the day, you see the effects of the atmosphere in the form of weather clouds form. Winds blow, temperatures rise and fall. But at night, the atmosphere tells its quieter stories, using stars as its canvas. Sometimes when the air is especially stable, the stars seem steadier, This might happen after a storm has passed, or when the wind dies down, and the air above you becomes still and layered. On those nights the stars sparkle less. But on restless nights, when warm and cool air chase one another across the sky, the twinkling becomes more dramatic. This ever-shifting nature of the atmosphere also means that where you are matters. Higher elevations, for example, often offer clearer views of the night sky. Why? Because there's less atmosphere above you to scramble the starlight. That's why observatories are placed on mountaintops, places like Mauna Kea in Hawaii or Cerro Paranal in Chile. Up there, the sky is less watery, so the stars can shine with less distortion. Even humidity plays a role. Moisture in the air can scatter light, creating halos or making stars appear softer, dimmer, or more diffuse. You might not think about water vapor when you're watching Orion climb the sky, but it's there quietly, shaping what you see. And here's a gentle paradox: while the atmosphere distorts our view of stars, it also protects us. It filters out dangerous radiation, moderates temperatures, and gives us the breathable air we need to lie under that sky and wonder in the first place. Isn't it strange how something can both blur and bless? So the next time you see a star flicker like a tiny flame, remember it's not the star that's dancing, it's the sky. It's your own planet's breath, moving between you and the cosmos, painting shimmer onto the points of light. You're not just watching the stars, you're watching Earth whisper to them. And that whisper, warm, alive, and fluid, is what makes the stars sing you to sleep. Let your eyes trace one of those shimmering lights above you, now just one. A single glint among the rest. It flickers delicately, a wink, a blink, a twirl of silver blue. From your quiet place beneath the sky, it seems impossibly small, almost fragile. That's because it is. Not the star itself, of course. The actual star may be a raging furnace 10 times the mass of our sun, burning with a temperature of tens of thousands of degrees. But the image you see, the light that reaches you, is a tiny, trembling pinprick. That's the nature of stars. They are so far away, some hundreds, others, thousands, even millions of light years from Earth, that their light arrives as a single point. Not a beam, not a spread. Just one narrow shaft of ancient brightness, focused and alone. Imagine shining a flashlight across an entire ocean, and at the far side someone sees only the tiniest dot of your signal. That's how stars behave. Each one sends its light through the vacuum of space, and when it touches your eye, it appears no wider than a needle's tip. This is why stars twinkle. Because that small focused ray of light has no room to adjust. When it bends even slightly due to the atmosphere's whims, it seems to jump or fade or change hue. There's no backup beam, no extra size to spread the effect out. Just that single wobbly pixel of brilliance. And it only takes a millisecond of distortion to make that star appear to dance. Now imagine looking at thousands of such pinpricks all at once. The result is a sky that shimmers and fizzes softly like a soda just opened or glitter caught in a breeze. Every star telling its own story, every photon shaped by its journey through the living, moving air. Ask yourself, how does it feel, knowing that some of the stars you see tonight no longer exist, their light still traveling across vast cosmic highways long after the star itself has dimmed? Does it make the flicker seem more mysterious or more sacred? And have you ever noticed how the fainter stars seem to twinkle more? That's not just your imagination. Dimmer stars produce less light for your eye to catch. That makes them more sensitive to atmospheric shifts. Each flicker becomes more noticeable. Your eyes are also constantly adjusting, scanning, compensating, and that micro-adjustment adds to the shimmer. Now and then you might spot a particularly restless star, one that seems to vibrate with chaotic energy, pulsing rapidly in color and brightness. But remember, the star itself isn't changing at all. It's just the path of light, the interference that causes this apparent drama. And here's something a little mind-bending. Even the color of a star can affect how it twinkles. Shorter wavelengths of light like blue and violet are more easily scattered than red. So blue stars often appear more shimmery, especially near the horizon. They dance with a higher frequency, a sharper edge. Now pause for a moment. Breathe in. Feel the thought drift by. Every twinkle is a map. Yes, astronomers can use the pattern of a star's flickering to learn about the layers of air above us. High-altitude wind speeds thermal gradients. Pressure zones, each one leaves a fingerprint in the twinkle. A tiny meteorological report written in starlight. Isn't that astonishing? You're not just gazing at beauty. You're witnessing data. Shimmering science disguised as bedtime wonder. Some observatories even use something called a scintillometer to measure the intensity of twinkling across specific stars. These instruments read the frequency and amplitude of starlight distortion, how fast it flickers, how deeply it fades, and from that they draw conclusions about the atmosphere. So that little dot you were tracing a moment ago, it might be helping scientists build climate models, or monitoring jet stream turbulence, or even helping satellites calibrate their lenses, all from a single glittering point in the sky. Stars, it turns out, are messengers, not just of ancient light and cosmic origins, but of the air between us and them. The smaller and farther the star, the more delicate its message becomes. But with the right tools and the right kind of listening, we can hear it whispering. And you're listening too, in your own way, through calm and curiosity, through that soft awareness that lives just before sleep. You're tracing twinkles, not just with your eyes, but with your wonder. You're feeling the night, not just seeing it. So as the stars above continue to blink, their tiny signals, remember this. Every pinprick of light is a window not just to the cosmos, but to the air, the science, and the soft shifting ocean that carries it to your dreaming eyes. Now shift your gaze just slightly away from that flickering tapestry of stars. See that light. Steady warm, a bit larger than the rest. It doesn't dance. It doesn't flash red and blue. It glows calm and unwavering, like a quiet thought holding its breath. That's a planet. And planets don't twinkle. Not in the way stars do. Not to the naked eye. They stand apart not by their brightness, but by their stillness. Their light seems sure of itself, like they're not showing off, just being. So why is that? Let's take a closer look, not just with our eyes, but with curiosity. Why does something so far away shine so steadily when stars, which are often much larger, can't hold their sparkle still? The answer lies in apparent size, not real size, because planets are dwarfed by stars, but how large they appear to us from Earth. It's all about the angle, the distance, the geometry of space. Picture a flashlight and a spotlight. Shine both at a faraway wall. The flashlight's beam will form a tight, concentrated dot. The spotlight will spread, even if just a little. Now imagine trying to distort those beams with a hand waving in front. The flashlight flickers easily. Its narrow beam is more vulnerable. The spotlight, less so. Its broader light can blur but doesn't flicker. Stars are the flashlight. Their light arrives in a single focused beam, a pinprick, a photon thread. But planets are like that soft-edged spotlight. Their light, though dimmer in origin, appears larger in the sky. That gives them resilience. Technically, planets like Venus, Mars, Jupiter, and Saturn subtend in angle a small but measurable size when seen from Earth. That means the light from a planet doesn't come from one precise line, but from a spread of paths, a gentle, steady wash. So when turbulence in the atmosphere bends the light, the effect gets averaged out. One wave of air might tilt one part of the planet's image slightly to the left. Another part gets tilted to the right. The end result, stability. This is why Jupiter hangs in the sky like a pearl, why Venus glows like a lantern, why Saturn beams with a golden hush. Not because they're immune to the atmosphere, but because they're big enough in your sky to shrug off its restlessness. Have you ever wondered why planets seem brighter than most stars, even though they don't produce their own light? It's because they reflect sunlight and do so from close by. Venus is just 40 million kilometers away at its nearest. Jupiter, around 590 million kilometers. Those may sound like astronomical distances, and they are, but compare that to the nearest star Proxima Centauri, over 4 light-years away, or about 40 trillion kilometers. That difference is everything. Even though the light from a planet is reflected borrowed light, it arrives to us in far better condition. Fewer obstacles, more signal, less distortion. It's like the difference between hearing a friend's voice in the next room versus across a canyon during a storm. The friend in the next room, you hear them just fine. So here's a lovely irony. Stars create their own light through nuclear fusion, releasing tremendous energy at their core. Planets simply borrow the light of their star. And yet, it's the planets that appear calmer, more reliable to our eyes. The humble reflectors, not the blazing beacons, earn our trust. It makes you think, how often in life do we mistake flicker for fire, drama, for importance? Maybe the calmest lights are the ones worth watching. Planets, too, have a way of moving that reveals their nature. Unlike stars, which stay locked in their constellations, planets wander. The word planet itself comes from the Greek planets, meaning wanderer. Over days and weeks, they shift slightly in the night sky, passing among the familiar patterns of stars, like guests moving through a party. Have you ever noticed that movement? Maybe you looked up night after night and saw a particular star drifting closer to the moon or edging past Orion's belt. That's how ancient sky watchers first understood that some lights were different. Different in path, different in behavior, different in how they twinkle or don't. So tonight, when you gaze up and spot a light that holds steady, that doesn't blink or sparkle like the rest, you can whisper to yourself, that one's a planet. It's not just a point, it's a presence, and it's stillness. That's a sign of nearness. A sign of the way it fills just enough space in your eye to steady the wavering breath of Earth's atmosphere. Think of it like this. Stars are like distant singers, beautiful, trembling their voices, shaped by the winds of space. Planets are the steady chords beneath them, quiet, dependable, glowing, not for attention, but for clarity. And in the hush between their songs, you find a lullaby. Now let's glide down slowly, dreamily, into the atmosphere again. This time, not just to notice that it moves, but to trace the journey of light as it falls from space toward your waiting eyes. Light, after all, doesn't just appear, it travels. It threads its way from the depths of the cosmos, streaming for years or centuries through the vacuum of space until right at the end it meets us. But Earth doesn't offer a smooth welcome. Instead, that light must pass through an ever-shifting, multi-layered sky, a stack of invisible blankets draped around the globe, each with its own character, its own rhythm. And as light passes through each one, it bends, slows, and shivers in ways that turn a steady beam into a living flicker. The uppermost layer it enters is the thermosphere, where auroras dance and charged particles fly. Then the mesosphere, where meteors begin to burn. Down through the stratosphere with its ozone veil, and finally into the troposphere, our weather layer. the one you breathe in, the one that touches your skin. And it's in these lower layers, especially the troposphere, where the real distortion begins. You see, light doesn't bend unless something tells it to. In a vacuum, it moves straight like a confident arrow. But in air, the game changes. Because air isn't uniform, it's messy. It's filled with pockets of warm and cool gas, with updrafts and eddies and turbulence. As warm air rises and cool air sinks, these layers mix. That mixing changes the density of the air, and with it, the refractive index, how much light bends as it moves through it. Think of the atmosphere as a river full of swirling currents. Light tries to cross, but each ripple nudges it a little off course. And because light travels so fast, nearly 300,000 kilometers per second, even the tiniest change in direction shows up to your eyes as a flicker. But here's the beautiful part. Every single star above you is undergoing this distortion, constantly, every night. And it's not chaos, it's a patterned kind of dance. Each star's light, refracted slightly differently, performs its own solo in the orchestra of the sky. And yet, we don't see the distortions happening. We see their result, the twinkle, the shimmer, the sparkle that seems to pulse in time with your breathing. It's a gentle illusion born from the structure of air. Now imagine the starlight as a traveler, tired and ancient, descending toward Earth. It's been flying straight for 1,000 years, no interruptions, no turbulence. And then bam, it hits the upper atmosphere, and suddenly the road gets bumpy. Winds push and pull. Warm air tosses it upward. Cold air tugs it sideways. And that pure straight beam of light begins to stagger. From your point of view, the star shifts. Not much, maybe 1,000th of a degree, but just enough. Your eye notices. Your mind notices. You perceive it as a twinkle. And now let yourself ask, does the twinkle mean the star is unsteady? Or is it you, or rather the air around you, that's making the change? Does the atmosphere color the truth, or show it? Here's where things get even more dreamy. The amount of twinkling depends on how much atmosphere the light must pass through. So stars overhead directly above you twinkle less than stars near the horizon. Because the stars closer to the horizon shine through a thicker slice of sky, a longer diagonal path through the air. It's the same reason the sun appears more orange and red at sunset. The light is filtered through more air, more particles, more variation. So the next time you look up and see stars near the horizon flickering like mad, while those high above hold their light, more steadily you'll understand you're not imagining things. You're watching physics in real time. And there's a hidden poetry to it too. Stars that sit high in the sky, the ones you see around midnight, perhaps directly overhead, those are speaking to you more clearly. Their messages are less altered, less scrambled by air. The higher they are, the closer you are to hearing their true voice. But stars near the edges, they're the dreamers, the ones who must shout across a crowded room, their voices warped by the movement between you. And yet both are beautiful. Both have their part in the night's lullaby. Now picture this, a sky filled with stars, each one filtered differently by the currents of air, each one performing a soft light show of imperfection. And beneath it, you lie in the stillness of night, listening with your eyes. Light dancing through an ocean of air, a journey that ends with you. Now that you're gently floating among the stars and their shimmering beams, let's drift deeper into a question you might not have asked yet, but one you've likely felt. Why do some stars twinkle wildly while others barely flutter? It's not your imagination. Some stars do indeed shimmer more dramatically than others. You may notice one in particular that flickers like a tiny disco ball. Colors shifting, light, jumping, brightness pulsing. Another nearby might hold steady calm and faint, like it's barely breathing at all. What gives the answer lies in the subtle geometry of the sky and the ever-restless personality of Earth's atmosphere. The way you see a star depends on where it is in the sky and how much air its light has to fight through to reach you. Let's imagine the sky as a giant dome above your head. If you were to lie down and look directly upward at what's called the zenith, you'd be seeing through the shortest path of atmosphere, just a thin column of air between you and the stars. But if you turn your gaze toward the horizon, your line of sight cuts diagonally through much more atmosphere, like peering through the length of a swimming pool instead of just the surface. More air means more distortion, more pockets of temperature difference, more turbulence. So stars close to the horizon will twinkle more. They must shine through more shifting air to reach you. This is why Sirius, the brightest star in the night sky, sometimes looks like it's strobing in red, white, and blue when it's low in the sky. But when it rises higher, it steadies. It's not Sirius changing, it's the air. Ask yourself this: have you ever seen a star change color in the span of seconds? Flickering like a ruby, then sapphire, then gold. That's atmospheric refraction at play, breaking white starlight into its spectrum, then scrambling those colors moment by moment. Now consider altitude in another sense, not of the stars, but of you. If you were to climb a mountain, say, 3,000 meters above sea level, you'd be above much of the thickest air. There's less atmosphere between you and the stars. So what happens? Less flickering, crisper points of light, clearer skies. This is why professional observatories are often built on high peaks, places like Mauna Kea in Hawaii or La Silla in Chile. Up there above the moisture and smog and turbulence, the stars speak more directly. And there's one more element to this celestial drama: the star's own brightness and position relative to the equator. Stars that lie close to the celestial equator tend to follow longer, smoother arcs across the sky. In tropical regions, they rise nearly straight, up past high overhead, and set directly opposite. Their path through the air is short and stable. But stars that linger low on the horizon, those near the celestial poles, must arc sideways across more of the atmosphere. So their twinkle is more erratic, their colors more variable. Even the star's temperature and light spectrum matter. Hot blue stars emit shorter wavelengths of light, which scatter more easily in air, meaning they may twinkle more than redder stars. It's the same reason the sky is blue. Short wavelengths scatter more, giving the atmosphere a bigger playground in which to bend and shake the light. So if you ever find yourself tracing two stars, one red, one blue, and wondering why the blue one seems to dance more frantically, now you know. The sky plays favorites, and you're watching its choices unfold. Let's not forget the size of the star's image as it appears in your eye. Brighter stars seem larger, not because they are, but because they create more intense signals in your retina. Ironically, this can make them appear to twinkle more, but also makes it easier to spot tiny color shifts, revealing how complex and layered their dance really is. So the next time you're outside, let your gaze wander across the sky. Try comparing stars high above you with those near the horizon. Track the flicker, the shimmer, the rainbow ripple. It's a gentle, silent lesson in physics, a reminder that every light you see is shaped not only by where it comes from, but by how it travels through the air above you. Ask yourself, what would the sky look like without an atmosphere? Would stars stop twinkling altogether? The answer is yes, and we'll explore that in time. But for now, rest in the knowledge that twinkling is not a flaw, it's a signature. A dance choreographed by Earth's breath, a performance shaped by temperature and angle distance and density. And it changes every second. In other words, No two twinkles are ever the same, and somehow that makes them feel even more alive. Now close your eyes just for a moment, not to sleep yet, but to feel the idea I'm about to share with you. Imagine the sky without an atmosphere. No wind, no clouds, no moisture, no breath between Earth and space. Just pure vacuum above your head. What would it look like? Well, oddly enough, stars would stop twinkling. In space, the sky is utterly still. Light travels in a straight, unwavering line from source to observer. No bending, no flickering, no sparkle. The stars become clean, constant pinpoints. Sharp, cold, and still. That's what astronauts see. From the International Space Station orbiting above 90% of the atmosphere, stars don't shimmer. They shine steadily, clearly, quietly, as if all the sparkle has been rinsed away. It's beautiful, yes, but also strangely sterile, almost too perfect. Up there, it's the stars themselves that reveal their personality, not the air between. You see, on Earth, our atmosphere acts like a filter, but also like a translator. It takes the cold, silent signals of distant stars and gives them motion-life feeling. The twinkle is the sky's voice, turning physics into poetry. So now ask yourself this: if twinkling is caused by our atmosphere, then what would stars look like from the surface of another world? Say Mars. Let's go there together for a moment. Picture yourself standing on the Martian surface, bundled in a warm, pressurized suit, boots pressing into rust-red dust. Above you, a sky that glows not blue, but butterscotch. Thinner than Earth's, drier, laced with carbon dioxide and streaked with occasional wisps of high-altitude clouds. Would stars twinkle? They might, but only slightly. Mars has an atmosphere, but it's just 1% the pressure of Earth's. That means far less air to bend the light, far fewer distortions to create the shimmer. The stars above Mars would appear mostly steady, like they do from space. Perhaps with a faint flutter here and there, but mostly still. Now think of Venus, our neighbor, in the opposite direction. Her atmosphere is incredibly thick, nearly 90 times denser than Earth's, and composed largely of carbon dioxide. Cloudy, opaque, hostile. On Venus's surface, sunlight itself barely makes it through. And the stars, you wouldn't see them at all. The sky is always hidden in toxic fog. No twinkle, no sparkle, just haze. How about the moon? There's no atmosphere at all. None to bend the light, none to refract. Stars shine like fixed needles in velvet. You could hold up your hand and block one out, and it would vanish without fluttering like a light behind a shutter. The same goes for Mercury. So we return to Earth. Our planet, the only one we know of where the atmosphere dances just enough to distort, but not enough to erase. The only one where you can lie on your back and watch the stars perform like fireflies caught in an invisible stream. Isn't that incredible? The twinkle of stars, something we so easily take for granted, is actually a rare and fragile thing. A quirk of our sky, a signal that you are home. If Earth's air were just a little thinner, you might lose the shimmer. If it were denser, you might never see the stars at all. But here we are in a sweet spot of science and softness, where starlight sings its way through just enough turbulence to make us wonder. And even more amazing, we use that twinkle to learn. Astronomers have created tools to measure the shimmer of starlight, to correct it, and even to remove it in telescopes. But in doing so, we've also learned to study the atmosphere itself by how it shakes the stars. That's the heart of something called adaptive optics. These are special systems built into high-powered telescopes, ones on mountaintops, often that detect the distortion caused by the atmosphere in real time. They use lasers to measure how the air is bending light at that moment, and then flex mirrors inside the telescope to compensate. These mirrors adjust hundreds of times per second, smoothing out the twinkle and bringing the stars into crystal clarity. It's like a telescope that can see through a swimming pool, as if it were glass. And yet, part of you might miss the shimmer, right? Because even though scientists want to see the stars exactly as they are, you might want to see them as they appear alive, moving, singing their lullaby of light through Earth's breathing sky. So as you lie here now, eyes open or closed, take a moment to appreciate the sky as it is. Not perfect, not static, but moving, whispering, flickering just enough to feel real. The stars don't need to twinkle, but your sky chooses to let them. You might be wondering now if the atmosphere is responsible for the twinkling. How do astronomers manage to study the stars with any precision at all? After all, a constantly dancing point of light isn't exactly ideal when you're trying to measure a planet's orbit, or the temperature of a stellar surface, or the wobble of a distant star that might hint at a hidden exoplanet. And yet, here we are, able to read the chemistry of stars, measure their ages, map their galaxies, and even detect worlds so distant they're smaller than a grain of sand seen from a mile away. How the secret is in technology that listens deeper than the Twinkle telescopes that adapt, correct, and reach above the air. Let's start gently with the oldest workaround. For centuries, astronomers simply built their observatories at high altitudes where the atmosphere is thinner and steadier. Mountains, desert plateaus, remote volcanic islands. Anywhere the air flows smoother and there's less light pollution. Even a few thousand meters above sea level makes a profound difference. The fewer atmospheric layers above, the fewer chances for turbulence to twist the incoming light. But of course, even the clearest mountaintop isn't immune. The air still moves, still breathes. Stars still flicker. So what did scientists do? They got clever. They developed a system called adaptive optics. A beautifully simple idea that turns twinkling into clarity. Picture this: you aim your telescope at a star, but the image keeps shifting slightly due to the air's movement. Now imagine you fire a laser into the sky, a perfectly timed pulse of light. This laser creates a glowing dot high in the atmosphere, a sort of artificial star. Then, using high-speed sensors, the telescope reads how this artificial dot is distorted by the air. The system calculates how the real starlight must be getting bent in that same moment. And then, a mirror inside the telescope bends itself. It changes shape hundreds of times per second. It flexes and warps so precisely that it cancels out the distortions in the starlight, like noise-canceling headphones but for vision. The result: the star stops twinkling, at least from the telescope's perspective. Its light becomes steady, sharp, and ready for study. But we didn't stop there. The next leap was to leave the atmosphere behind altogether. This is why we built the Hubble Space Telescope, and later, the James Webb Space Telescope. These instruments float in space far above Earth's sky, completely beyond the reach of turbulence. No atmosphere to bend the light, no air to scatter colors. Just pure starlight uninterrupted. From that vantage point, stars appear perfectly still. Their light is clean focused, like a song played without static. We can detect chemical signatures, the faint glow of galaxies born billions of years ago, even the trace of atmospheres around alien planets. But for all that clarity, there's still something magical about what we see from Earth. The shimmer, the movement, the soul of the sky. You might ask yourself if technology can erase twinkling, should it? It's a fascinating question. Because while astronomers need to eliminate distortion to make precise measurements, we, the casual stargazers, the sleepy scientists lying under blankets and constellations, might find that the imperfection is part of what makes the night feel alive. After all, a motionless sky might be scientifically ideal, but a shimmering one stirs emotion. It tells us the air is moving, that we are inside something not apart from it, that the universe is not just out there cold and still, but here with us touching the light we see whispering through it. And sometimes what moves you isn't the clarity of the data, it's the quiver in the song. Even in the age of space telescopes, amateur astronomers and sky watchers still cherish the way the stars appear from Earth's surface. That moment when a child spots Sirius and says, "It's sparkling like a diamond," or when an elder traces the same constellation they saw from a field decades earlier, still blinking softly in the dark. Twinkling is memory, it's motion, it's a sign of presence. So maybe the role of science isn't to remove the shimmer, but to understand it, and then choose how we see it. You tonight are choosing to see it. You're lying beneath the sky, listening not just to facts, but to feeling, to flickers, to the science of air wrapped in the softness of wonder. So whether your stars tonight are bouncing wildly or barely trembling at all, know that this flickering is not failure. It's evidence of life between you and the universe, a gentle proof that you're here and that the stars are still reaching through the breath of Earth to reach your eyes. Let's take a moment to look even closer, not just at the stars or the planets, but at the very nature of light itself as it travels through Earth's atmosphere. Light is not just a simple beam. It's a wave, a gentle ripple that can bend, scatter, and even split into colors. When light from a star reaches your eyes, it's arrived after traveling across unimaginable distances. But before it can reach you, it must navigate a maze of air pockets and temperature shifts, which cause that familiar twinkle. The process that causes this is called atmospheric scintillation. It's a fancy term that means light is flickering, because the atmosphere is bending it like a funhouse mirror. But there's more to it than just bending. The light actually breaks into tiny parts, each traveling slightly different paths. Imagine a river flowing over rocks. The water splits and swirls around each stone. Similarly, light waves spread out, twist, and sometimes interfere with each other. This interference can make the star's light brighten or dim in an irregular rhythm. This rhythmic brightening and dimming is what your eyes perceive as twinkle. Have you ever wondered if this flickering might also have a sound? If the stars could sing the patterns of their light, the atmosphere's shifts are silent to us, but in another sense, twinkling is like a light song, a natural code written in fluctuations. Scientists use this phenomenon to study not just the stars, but the atmosphere itself. By measuring how much a star twinkles, they can infer details about the temperature gradients, wind speeds, and turbulence in the air above you. It's as if every twinkle is a whisper about the sky's invisible moods. Now consider the difference between stars and planets once more. Planets appear larger because their light comes from a disk, not a pinpoint. This means the light they send is less likely to be scrambled by the atmosphere, as different parts of the disk can average out the turbulence. It's like listening to a choir instead of a soloist. The collective voice is steadier. But what about stars that don't twinkle as much? Some stars are part of binary systems or even surrounded by clouds of gas and dust. These environmental factors can affect how their light travels. Others are simply brighter and appear larger, reducing their twinkle. And here's a fascinating fact: the human eye itself plays a role in perceiving twinkle. Our eyes constantly adjust focus and brightness, which enhances the flickering effect. Sometimes you might notice a star's twinkle changing as you blink or move your gaze. So next time you see a twinkling star, think about the journey its light took, not just through space, but through the complex living atmosphere around you, and even through your own eyes. This cosmic dance involves not just distant stars, but the very breath of Earth and your body itself. Isn't that a beautiful thought? Now let's turn our attention to one of the most enchanting sights in the night sky, the colorful twinkle of bright stars like Sirius Betelgeuse or Vega. Have you ever noticed how their twinkling sometimes seems to burst into reds, blues, greens, even purples? This sparkling kaleidoscope is a phenomenon called chromatic scintillation, and it's like the atmosphere's own light show. Light from stars is composed of all colors mixed together like white light from the sun. But when it passes through our atmosphere, the different colors, each a different wavelength, are bent by varying amounts. This bending or refraction depends on wavelength, with shorter wavelengths, blue and violet, bending more than longer wavelengths, red and orange. Picture sunlight through a prism breaking into a rainbow. The atmosphere is a much subtler prism, but enough to split starlight slightly as it reaches you. When the air is turbulent, this effect is more pronounced. Different colors seem to leap and dance independently, giving stars their twinkling rainbow halos. This is why stars near the horizon often seem to flicker with dazzling colors. Because their light travels through a thicker slice of atmosphere, the separation of colors is magnified. Interestingly, planets rarely show this colorful twinkle because, as we explored earlier, they appear larger in the sky, and their light is less affected by these small-scale atmospheric variations. Their light is more uniform, their colors steady, giving them that calm, glowing presence. Imagine a musician playing a violin perfectly steady versus one playing with fast vibrato. Stars twinkle with vibrant vibrato. Planets hold long, smooth notes. Now ask yourself, have you ever wondered if this colorful twinkle could actually tell us about the atmosphere's condition? At that moment, scientists think so. Changes in atmospheric turbulence and temperature gradients shift the colors and intensity of twinkle. It's a natural weather report written in light. Telescopes equipped with specialized instruments called spectrometers can analyze these colors, decoding the information hidden in the star's twinkle to better understand Earth's atmosphere as well as the stars themselves. This interplay between light and air makes every night sky uniquely beautiful, a constantly changing masterpiece. So the next time you see a star flash with red, green, and blue sparks, think of it as the atmosphere's quiet fireworks, nature's way of reminding you that even the coldest points of light are warm with life. And don't you love the idea that the twinkle is not just a trick of light, but a message, a colorful wink from the cosmos? It's as if the stars themselves are flirting with you, shimmering not just to be seen, but to be felt. As you continue drifting beneath the night sky, you might start to notice something else, something quieter, subtler. Some stars don't just twinkle, they pulse. Their brightness rises and falls in slow, deliberate waves, not from the atmosphere, but from within. These stars are not just dancing with the air, they are dancing with themselves. Welcome to the world of variable stars. Unlike twinkling, which is caused by Earth's atmosphere, bending light variability in these stars is intrinsic meaning. It's caused by changes happening inside the stars themselves. Their brightness really is changing, not just appearing to. Have you ever seen a star that looks a little different? Each night, brighter one evening, dimmer the next. Perhaps you thought it was your eyes or clouds. But no, it could have been a variable star whispering in its own internal rhythm. There are many kinds of variable stars, but let's explore a few of the sleepier, dreamier types, the ones that feel like they're breathing in the darkness. First, there are pulsating variables, like Cepheid variables, and RR Lyrae stars. These stars literally expand and contract over time, like a slow heartbeat. Their outer layers swell outward, then collapse inward in cycles that can range from hours to months. Imagine a star as a softly glowing lung, inhaling and exhaling its light across space. As the star expands, its surface cools slightly and dims. As it contracts, the heat intensifies and the brightness surges. These shifts are measurable, and more than just fascinating, they're deeply useful. Cepheid variables in particular are like cosmic lighthouses. By studying how long their pulsation cycle takes, astronomers can calculate their distance. That's right, these twinkling breaths help us map the universe. Now there are also eclipsing binary stars, two stars that orbit each other, passing in front of and behind one another, as seen from Earth. When one star blocks the other, the total light dims like a gentle wink across time. Their light doesn't flicker randomly, it fades and brightens like the slow pull of tides. And then there are the irregular variables, stars, that change brightness due to massive sunspot activity, magnetic storms, or chaotic outer layers. These are like the moody poets of the cosmos, full of unpredictable emotion, flaring and dimming without warning. One famous variable star you may know is Betelgeuse, the reddish shoulder of Orion, a supergiant nearing the end of its life. Betelgeuse dims and brightens noticeably, even with the naked eye. In late 2019, it dimmed so dramatically that scientists wondered if it was about to explode in a supernova. Spoiler alert, it didn't. Not yet. But it reminded us that stars aren't just points of light. They're living entities with cycles, rhythms, and sometimes endings. Isn't that humbling? All this, these internal pulses, these eclipse dances, these fading flares, they happen on top of the atmospheric twinkle. So sometimes when you watch a star blink and shimmer, you're seeing a double layer of beauty. Earth's breath and the star's own. Have you ever thought about how many types of change are layered into a single flicker of starlight, and how many of those are messages from across the galaxy? The next time you catch a star that doesn't behave quite like its neighbors, one that glows a little more red or seems to swell and fade, over days stop and wonder, is this star telling me something older, something internal? And what might its rhythm say about the scale of time? Here on Earth, your breath rises and falls every few seconds. The tide comes in and out every 12 hours. But a Cepheid variable might pulse every 5 days. A binary eclipse might take 3 weeks. A massive supergiant like Betelgeuse could fluctuate over 400 days or more. And somewhere a planet like ours is surely watching, wondering, waiting for its own sky to shimmer. So tonight when you see a star that's bright and steady, or one that pulses faintly like a heartbeat in the sky, know that you're watching a rhythm older than memory. A lullaby sung not in seconds or minutes, but in centuries. Let's float gently now, so gently into the space between the stars. Because as you've learned, twinkling tells us something about light, the air, and even the stars themselves. But what if the light had to pass through something else on its way to you? Yes, the Earth's atmosphere causes the familiar flicker. But in the vast distance between the stars and our little blue planet, there's more than just emptiness. There are clouds, not clouds like ours filled with raindrops and cotton fluff, but cosmic clouds, wisps of dust and gas stretching across light years. These are known as interstellar medium, and when starlight travels through these regions, it can scatter red and dim, or even disappear entirely. But not twinkle. That's an important detail. The twinkling that sparkles above you each night is something intimate, something local. It only happens in the last instant of the light's long, long journey, when it brushes against the breath of your own world. But what happens farther out changes the character of that light, not its shimmer. Still, we must take a dreamy detour here, because some of the most beautiful effects in the night sky come from these invisible veils floating between the stars. Take nebulae, for example, vast clouds of ionized gas that sometimes reflect, sometimes emit, and sometimes absorb starlight. When starlight passes through a diffuse nebula, it can become reddened, its blue wavelengths scattered away just as our own sun appears redder at sunset. This process is called interstellar reddening, and while it doesn't cause twinkle, it does add a softness, a hush to the light. Stars seen through a veil of cosmic dust can appear dimmer, warmer in color, like the fading glow of a lantern behind frosted glass. You might ask, do these distant dust clouds ever make stars seem to shimmer? No, not in the way you're used to. Unlike Earth's atmosphere, these clouds don't change rapidly enough or move irregularly enough to cause the light to flicker moment by moment. Their effect is slow, stable, a quiet murmur rather than a sparkling song. But there's a different kind of starlight drama we sometimes get to witness: gravitational lensing. Imagine a star's light heading toward Earth only to pass near a massive object like a galaxy or black hole on the way. The gravity of that object bends the light around it like a magnifying glass. Sometimes this even creates multiple images of the same star or causes its brightness to briefly surge before fading again. This sudden change in brightness is called microlensing, and it can happen unpredictably, lasting hours, days, or even longer. And though it's not technically twinkling, it feels like a kind of cosmic flicker, as if the universe is playing hide-and-seek with the stars. You, the quiet stargazer, may never spot one of these microlensing events without a telescope. But just knowing they happen, knowing that space itself can bend and shape light, adds another layer to the wonder. So think of the journey a star's light must make. It might pass through the cold silence of interstellar dust, softening and reddening as it goes. It might slip by a dense star cluster, its path slightly tugged by gravity. It might even thread the edge of a black hole, its light stretched, distorted, but still intact. And after traveling for thousands, even millions of years, that light arrives here into Earth's atmosphere, and only then does it begin to twinkle. Isn't that remarkable? All that distance, all that time, and the flicker you see is not the story of the star's struggle to be seen. It's the story of your sky shaping the last moment of that journey. It's almost like the universe whispering, "You're part of this too." So as you lie back now and the stars shimmer above you like a field of blinking fireflies, remember that their light has traveled farther than any sound, any wind, any bird or cloud, and that the twinkle, the very last thing that light does before it reaches you, is dance. As we drift deeper into this night of soft discovery, your mind might start to trace a curious question. If stars twinkle and planets don't, how do we actually tell them apart with just our eyes? You've likely been stargazing before, standing under a quiet sky, gazing upward at a sparkle here, a steady glow there, and wondered, which of those is a star and which is a planet? It's simpler than you might think, and beautifully poetic. Because twinkling isn't just a side effect of the atmosphere. It's also one of the sky's secret codes, helping you distinguish the ever-burning stars from the softly glowing planets. Start with this. If a point of light is twinkling rapidly, especially when low on the horizon, shifting subtly in color, you're likely looking at a star. If instead, it shines steadily, like a pearl suspended in darkness, with a soft, unwavering glow, it's probably a planet. Venus, for instance, known as the evening star or morning star, doesn't twinkle. It glows calm, bright, serene. Jupiter, too, often outshines the stars around it, but its light is consistent, almost soothing. Saturn, a little dimmer, still holds that same peaceful steadiness. That stillness is your giveaway. Planets appear as tiny disks through the atmosphere, still very small to the eye, but large enough that atmospheric turbulence affects different parts of their image at once, effectively averaging out the distortion. Stars, by contrast, are so far away that they appear as true point sources, tiny singular dots of light. There's no surface area to average, so every little ripple of the air tugs them one way then another. They flicker like candle flames caught in a whisper of wind. And here's a sleepy trick next time you're outside. Hold your gaze steady on a bright point in the sky. Watch for flicker. Now shift to another. Is it steadier? Glimmering less? You may have just compared a star with a planet using nothing but your breath and your eyes. But there's another layer too. The planets also move differently. While the stars rotate across the sky in fixed patterns locked in place by the constellations, the planets wander. The word planet comes from the Greek planets, meaning wanderer. And that's exactly what they do. Over the course of nights or weeks, you'll notice them drift slowly against the backdrop of the fixed stars. Sometimes they even appear to reverse course for a while in what's called retrograde motion, a trick of perspective as Earth passes them in orbit. So if you ever see a bright object that stays low in the western sky night after night, not twinkling and inching slowly along the ecliptic path, the invisible highway of the solar system, it's likely one of your planetary neighbors. You might now be asking, are there exceptions? Can planets ever twinkle? On rare occasions, yes. When a planet is very close to the horizon, especially in turbulent air, you might see it flutter just a little. But this is the exception, not the rule. The steadiness of planets is one of their defining features to the naked eye. And this distinction, twinkling versus stillness, has helped skywatchers for thousands of years. Long before telescopes, ancient astronomers tracked the planets using their unique calm glow. Venus rising before dawn, Mars turning red in the night, Jupiter looming bright and low in the east. No twinkle, just presence. So the next time you step outside, find one bright point of light and simply watch. Does it shimmer and dance like it can't quite hold still? Or does it shine like a steady thought, unwavering waiting? One is a star singing through the turbulence of air. The other, a planet glowing softly through the veil. You've learned to listen, and the sky has always been ready to speak. Let's take a deep breath now. One long, slow inhale, and drift even farther back in time. Because long before we had science to explain why stars twinkle, people were already watching the sky and weaving stories from the shimmer. Twinkling stars weren't just lights. They were eyes, souls, omens, gods. Across cultures and centuries, people have looked up at the night and found meaning in the flicker. That subtle, wavering glow became a canvas for myth, a signal from the heavens, a bridge between earth and sky. In ancient Egypt, the twinkling of Sirius, the brightest star in our night sky, was far more than a visual quirk. Its annual rising shimmering low on the horizon just before dawn heralded the Nile's flooding the heartbeat of Egyptian agriculture and survival. The star's first sparkle through the misty dawn marked a new year, a sacred time of fertility and renewal. In China, astronomers recorded guest stars, new stars that appeared and twinkled brightly before fading. Some were supernovae, others variable stars. But they weren't just observations. They were heavenly messages, signs that the emperor must pay attention, that harmony or warning was being whispered through the cosmos. In Navajo traditions, stars were sewn into the sky by the holy people, their twinkling a kind of cosmic embroidery. Each shimmer was a sign that the world was being watched over, cared for. The stars flickered not from cold detachment, but from living spirit. Even in classical Greece, the philosopher Ptolemy noted how stars twinkled while planets did not. He didn't know why, not precisely, but he recorded it carefully, sensing that the difference mattered. He was watching the sky's language, even if he couldn't yet translate it. So twinkling became a kind of ancient code, not yet scientific, but certainly meaningful. And maybe that's something worth remembering. Because before we knew about diffraction and turbulence, before we built adaptive optics or launched telescopes into orbit, we still felt something true in the night sky. Something that couldn't be measured with instruments, but only with silence, breath, and wonder. Have you ever wondered why twinkling stars so often appear in poetry, in love songs, in nursery rhymes? Twinkle, twinkle, little star. That simple line isn't just for children. It's a quiet marvel passed down across generations. A reminder that this one small feature, this flicker, has connected us to the cosmos for as long as we've been able to look up. And now you know both sides of the story. You know the science, how molecules in the atmosphere bend the light, how different wavelengths scatter, how point sources shimmer while disks stay still. And you know the magic, the human feeling that rises when a star blinks through the air and somehow feels alive. You've crossed from myth to mechanism and back again, and both are true. It makes you wonder, doesn't it? How many other scientific phenomena have hidden poetry? The waves of an ocean might be kinetic energy, but they still sound like a lullaby. The aurora is charged particles colliding with magnetism, but it still looks like dreams come alive. And starlight flickering above you is just photons bent by air, yet it still feels like the universe winking at you. Maybe science doesn't take away the wonder. Maybe it gives it roots. So tonight, as you lie here beneath your own slice of sky, think about how many others have done the same. Thousands of years of necks tilted back of hearts listening to the light. Not just asking what it is, but asking what does it mean. And in that shared shimmer, one part physics, one part poetry, you find yourself part of the story too. And now here you are at the quiet edge of our journey. Eyes, heavy, mind still curious. And above you the stars continue to shimmer, like tiny lighthouses blinking through time and air and distance. So let's gather everything we've floated through tonight. Let it settle like dust on moonlight. You've followed light from stars as it travels unimaginable distances, slipping between galaxies, weaving through interstellar clouds, dodging gravity wells, and whispering past the cold emptiness of space. For thousands, sometimes millions of years, that light moves in a straight, unwavering line. Until the final instant. That last breath of its journey is through the atmosphere of Earth, a chaotic sea of moving air, layered in temperature, dancing in pressure. And that's where the twinkle is born. You now understand that twinkling is not a property of the stars themselves, but a poetic artifact of where you are, your atmosphere, your vantage point, your Earth. You've wandered with Sirius, and Vega paused with Mars and Jupiter, compared the stillness of planets to the shimmer of suns. You've felt how stars pulse with internal fire, how some fade, surge, or even vanish in bursts of light. You've heard the silence of space turned into a melody by air. And perhaps just gently, you've begun to feel that twinkling is more than a quirk of optics. It's a gift of perspective. The very thing that distorts your view also reminds you that you are not outside the cosmos looking in. You are within it. Your eyes, your breath, your atmosphere, all part of the story, part of the movement, part of the glow. Ask yourself this: how often in life do we get to see something change simply because of where we are? And how lovely is it that this change makes the stars more alive, not less? The flicker of light overhead is a connection, a moment shared between you and a star that began its journey long before you were born, and arrives, now shaken gently by the sky, offered softly to your gaze. If you're still awake, you might picture it. Now a star's photon having traveled light years, bending ever so slightly as it hits a warm updraft over your rooftop. And that little shimmer, that's the story of everything. A universe that moves, a sky that breathes, and a quiet listener. Yes, you watching the stars becomes something more than just distant fires. Because to twinkle is to be seen, not perfectly, but intimately. And that, in the end, may be what makes the stars so special. You're not watching them through a flaw. You're watching them through a world that's alive. And now let's slow everything down. Let your breath melt into the rhythm of your own body, soft, slow, almost like waves lapping gently against a shore. The sky above you continues to shimmer, but you no longer need to look. The stars are there. They always are, twinkling just enough to remind you they're real. You've walked through science tonight, but also through feeling. You've touched the air with your imagination, followed light with your senses, and held distant stars in the cradle of your thoughts. Let that twinkle carry you. No need to solve anything now. No pressure to remember. The knowledge is there somewhere deep, humming like a lullaby just beneath your awareness. The sky doesn't ask questions. It simply invites. So sink into that. Let the stars recede. Let the colors soften. Let the shimmer dissolve into something slower, sleepier, safer. And if you're still awake, maybe tell yourself, this I am made of the same atoms that sparkle in the sky. Because you are. The stars that twinkle above you are your ancestors in light. And their glow, however small, finds its way to you, not despite the atmosphere, but because of it. The last flicker of starlight passes through the same breath that fills your lungs. You're not just under the sky, you're within it. If you've enjoyed this journey, I'd be quietly grateful if you'd give this video a like or tap that subscribe button for more peaceful explorations with the Sleepy Scientist. It helps more than you might imagine. And before you drift off, I'd still love to know, where in the world are you listening? From what time it is there? Leave a comment if you're feeling cozy enough to share. It's always a quiet joy to see this sleepy little community ripple across time zones and continents. Good night. Sweet dreams.